Okay, one moment. Has the slideshow begun?
Yes.
Yeah.
Okay. So I wanted to talk about my motivation for studying diffraction phenomena. Just start with the observation that in an asteroid star occultation, we get diffraction effects for free. I mean, more accurately, they're not optional. They stem from the physics of light and are therefore unavoidable. So an occultation timing extractor will at least sometimes need to take such effects into consideration. So I had these motivations for studying diffraction effects prior to adding that modeling to PyOTE. Number one, because of the great work by Dave Harold with the Gaia catalog and Steve Preston's efforts in refining predictions, I anticipated that there would be an increasing number of occultations that would exhibit significant diffraction effects. And number two, well, if diffraction is always present, why not always include those effects in the model light curve? If the effect is insignificant, no harm is done. But if the effect is enough to affect DNR timing, you will have automatically included a relevant effect. And then three, I needed to find out what minimal set of parameters needed to be specified by the observer in order to enable good model light curve generation. These are the references that I used in developing this talk and the diffraction modeling now incorporated in PyOTE. The first one, the Raymond Dusser reference, is well known in the occultation community, and I use his equation and nomenclature for what I refer to as the analytic diffraction light curve in the work that follows. It is a rather simple equation because all of the complicated approximations and computations are wrapped in Fresnel integrals for which there are publicly available functions for performing the needed calculations. The second reference from Michael Richmond, I'm following his recipe for including the effects of a finite star disk. And then finally, and this is really the most critical, I used Seymour-Trester's scheme for rapid calculation of Fresnel diffraction patterns of arbitrary shapes through use of a clever change of variables in a discrete, it's actually a discrete fast Fourier transform calculation. Recently, there's been an email thread about diffraction, and in that email thread came up a reference to the classic presentation in this field. It's a 1987 paper by, I think it's Roquez, R-O-Q-U-E-S et al. And that was really a tour de force, and it was a very difficult thing for them to achieve back in 1987. Now I've been able to reproduce their work with about 12 lines of Python code and some better computer hardware than perhaps they had available. I don't think that it's well known in the community that this tool for calculating diffraction is available. I know that one professor did reference it in his study of the atmosphere of Pluto. But I think otherwise it's not particularly well known. Now, this is the classic light curve that I think many of you have seen. This is almost directly out of Raymond Dusser. I should point out a few things about this. The plot assumes that only light of a single wavelength is present, and it assumes that the star is a point source and that the asteroid can be represented by an infinite straight edge. Now, of course, none of the assumptions behind this plot are actually present in a real occultation. So it's natural to ask whether this matters, and that's one of the questions that or some questions that I will address in this talk. In this plot here, the geometric edge is indicated by the vertical dashed line. the horizontal red line at the 25% intensity level intersects right at this point. That's at the 25% intensity, and should indicate that the way the math works out, that intersection point is not wavelength dependent. So the fact that this happens to be a plot made at a single wavelength is not relevant to where that intersection occurs. Now, I should say that you will unlikely ever find any of your occultations in which this intensity crosses at 25%. There is always something that messes that up. I should indicate that this plot is in units of Fresnel length. I used Fresnel units here, and that involves the light wavelength. And that is why a plot like this never specifies a wavelength. And I'll talk more about the Fresnel length in a bit. Let me move to the next slide. So my question is there a problem here? I mean, since most diffraction is discussed in terms of an example diffraction curve that assumes a single wavelength of light, a straight edge model of infinite, and those assumptions do a really tidy mathematical formulation of the problem. It's not our reality. So I'm going to ask the question, and I'm going to do the study to determine, do these differences matter? So the first step in the study was to take the Trester algorithm and write it in Python. Actually, I think he showed it in Python. That sort of made it easy. And my first test was to simply show a graphic. This is the target, and the target is a knife edge. You can consider it of infinite extent. It extends vertically. And to use the Trester algorithm to calculate the resulting diffraction pattern, which is shown on this right-hand image. I then plotted the dots show what happens when you take an intensity plot across, actually right across here, horizontally across the 0 level. And of course, it's shown in dots because this is a discrete Fourier transform. It's not a continuous one, and so it's done at finite points. And so that's why we have these blue dots. And through those blue dots, I have drawn the analytic straight edge from the Raymond-Dusser formula, and we see that the agreement, I don't think it could be much better. Now, the Fresnel length is commonly used, and I wanted to show the definition that I use. I believe it's the same one that Raymond-Dusser uses. Occasionally, you will see this without the division by 2. So you have to be a little careful to make sure that you're doing an apples to oranges. But the Fresnel wavelength involves the square root, or Fresnel length involves the square root of distance times another distance. So the Fresnel length is actually a distance. And so if you measure distance in kilometers and wavelength in kilometers, seems a strange way to do that, but in fact it works out, and you end up with a Fresnel length in kilometers. Now, I want to say that in addition, the significance of a Fresnel length, usually expressed in kilometers, is that most of the diffraction effects on the light curve occur within a region of 1 Fresnel length on either side of the geometrical edge. So that's where it swoops up from 0 to this peak, and then after that it rings. But most of the change that you see is within 1 Fresnel length on either side. In addition, that Fresnel length interacts with asteroid speed to give us what I will call a Fresnel time, which is the time for a unit Fresnel length to pass our observation point. So a Fresnel time is equal to the Fresnel length divided by the shadow speed. So that gives you a time. And when that Fresnel time is greater than our camera exposure time, diffraction effects will likely, not always, but will likely be present in the observed light curve. So the next thing I did to see if my code was working right was to pick a different object, calculate its diffraction pattern, and that just seemed reasonable. So I had some confidence that my code was working right. So now I needed to move on to something that is more real. So this is a picture of the diffraction pattern calculated using Trester's discrete fast Fourier transform method of an asteroid that had a diameter of 8 kilometers at a distance of 2.7 astronomical units. In this case, the Fresnel length turned out to be about 1/3 of a kilometer measured at 500 nanometers. I want to point out a few things about this. This is the green line shows the center line. If you were so fortunate to be on the center line, this is where you would be. I imagine that this asteroid is moving left to right in this manner. The geometric edge, if you were on the center line, occurs right here, which is, as you can see, still kind of in the dark region. And that is a common feature of diffraction. And you can see it from our diffraction curve. Now, most of us will not be so lucky as to be on the center line, and we'll be somewhere offset. And so there's actually a graze phenomena associated with diffraction, and that has to be taken into account because that distorts and stretches in kind of an odd geometric way the pattern of the light curve. Let's move on to the next graph. Here I did a line through the well, this is the light curve that would be seen by an observer who was located on the path center line of that previous slide. Again, the blue dots are discrete, again, because the calculation is a discrete calculation. And I am showing in this orange curve the analytic light curve from Raymond-Dusser. And again, we see that there is good agreement between those calculations. So here we had a round object. It wasn't an infinite straight edge, but when you were on the path center line, you saw a diffraction curve that was the same as though the asteroid had been actually an infinite straight edge in the sky. But what happens if that object was a relatively tiny object? That was a pretty good size asteroid that I chose. So I moved to an object that was small. In fact, it was so small that I decided it made more sense to show its diameter not in terms of kilometers. It was actually just under a kilometer, but to express it in Fresnel units. So this is what my target looked like, and this is its diffraction pattern. And of course, right here, we see what is commonly referred to as the Poisson spot. It is always present, or is frequently present, but it's very difficult to observe. You have to be in exactly the right place. So when you draw an intensity profile along this y equals 0 line right here, you get this blue line, and it's got lots of wiggles, and it goes through the Poisson spot. But when you do the analytic light curve, of course, it doesn't include a Poisson spot. That's not part of its math. But you can see that in general, the ups and downs, although they show some fine structure, they do in fact follow rather closely the analytic edge. Note you don't have to be far. I move off the center line by 1 Fresnel unit, so that's sort of like right here. So from here to about here. And of course, immediately what happens is you can no longer see that Poisson's point. It's just simply too small, and you miss it. And that's what frequently happens. Now, so far, all of the computations that I have performed have used a single length of light. So I now need to address that question. What I did here was I took a single wavelength analytic edge, and I calculated a large number of them over the 400 nanometer to 600 nanometer range, and I summed them all up and divided by the number to get the effect of a pass band. It's an odd pass band since it's 0 everywhere except at the 400 to 600 meter range. And we can see that in the region that we're most interested in, which is sort of like here to about here, there's almost no difference between a single wavelength analytic edge and the effect of combining multiple wavelengths. In fact, almost the only effect that you can really notice is a reduction in this, I'm going to call it ringing, that occurs after the event. I assume that if I continued adding more and more wavelengths, that this ringing would in fact continue to diminish. I did some experiments that way, and that was definitely the trend. Okay, so moving on to the next slide. So I started with a couple of questions, and I wondered about whether the single wavelength of light from the star mattered, because we see a pass band, and whether that straight edge model of the occulting body mattered. And I now have some answers, what I consider answers. I think what we saw was that there's just an insignificant difference between a single wavelength diffraction curve and one composed of a pass band, at least over that roughly 1 Fresnel length distance on either side. So that's definitely not a problem. Now, the straight edge model does not let us model off-center line observations, and that can result in significant timing errors. So that's a problem that must be dealt with. And so the question then is, can we use a diffraction model based on a generic round asteroid diffraction field, or must each asteroid size and shape be modeled uniquely? Well, I showed a big one and I showed a small one, and the answer, at least in my opinion, is we probably don't have to consider the very specific features of an asteroid shape, but if we encountered a high value, high quality, and reliably detailed observation of an odd shaped asteroid where there were significant diffraction effects, I know that's stacking up a lot of ifs. There is a tool available to assist the data analysis by calculating a bespoke diffraction field for that asteroid. I may take the time to package that calculation so that that tool will be available and people could kind of draw a picture of the proposed asteroid shape and get a diffraction pattern and extract light curves, and they could answer for themselves whether that was an important factor. So at this point, I want to move on to how this is being implemented in PyOTE. Now, one of the things I learned from the study was that I had to have this parameter. I had to be able to allow the user to specify how far off the center line he thought he was as part of the calculation of the model light curve. I've just extracted enough of the GUI of PyOTE so that those who have that program available can locate this easily. And I've actually filled in the numbers of what I'm going to show, although I won't show them all at once. I'll build them up bit by bit because I'd like to show how the model light curve gets built up. This demo button invites the user to play with these parameters. It's a good way to learn how things like your exposure time and the asteroid speed, its diameter, and if there was a finite star disk, how those affect the model light curve. So let me move on. Okay, so what I'm showing here, I'm only considering the effects of diffraction. So that's this green curve, and interacting with your camera exposure time, which acts as an integrator. And here I used a frame time of 150 milliseconds. When this exposure function is convolved, thank you, Michael Richmond, with the underlying light curve, the blue curve shows what you see from the camera response curve. Earlier, I commented that this intersection of the theoretical underlying light curve with the geometrical edge, which is this, which occurs at the 25% point, you don't see that. You don't see it because your camera integrates it away. And here it's showing up, I think this is about 47%. So that's a really, really common effect. Let me move, I'll add a little bit more. Here, I've added a finite star disk, not a big one, it's just 0.1 milliarc seconds, but you can see that that has a fairly dramatic effect on almost wiping out the diffraction effect. And I think it's important to keep in mind that even a very small star disk can have a large effect on the model light curve. The lesson here is that if you're expecting diffraction effects and you don't get them, think about having a previously undetected / unreported star disk as the cause. Okay, finally, I'm including the effect of a graze. So I'm letting the observation point be 4 kilometers off the center line, which is almost to the edge. This was a 10 kilometer diameter asteroid. So it had a radius of 5 kilometers and I'm 4 kilometers toward the edge. And the green curve here shows what the graze effect is. It takes the red curve, which is the underlying light curve, and it stretches it. It's not a linear stretch. It's a kind of an odd geometric stretch, but you can see that it slides the timing. And if you're able to measure the instantaneous intensity, that there's a timing difference here, which is some tens or maybe 100 milliseconds. So if you were actually able to have a sufficiently high signal to noise ratio observation, that graze effect could begin to affect you. Now, the example that I've shown, while it's visually compelling, in practice, it would require really a high quality observation, lots of transition points. It's something that happens slowly compared to your camera time. And it would need to be a low noise observation for there to be a statistically reliable difference to occur during the D and R time extraction. Still, it's nice to have the rigor applied always in any case. Now, I want to point out that although all of the displays that I showed a separate light curve for, I think I was showing the R side, but there is a plot for the R side and a plot for the D side, but they are always put together when the model light curve is fit to your observed, because that's the physics of the situation. You really should fit a light curve that matches the physics of the observation. So that brings me to the end of my presentation, which is questions. And I'd like to pose a question to the presenter. That's me. And my question is, Bob, do you have any examples to show us where the diffraction effect was important for the timing? Well, no, I don't. Bob, doesn't that sort of mean that you've got a solution in search of a problem? Well, in a way, yes. But I think the way in which this will most often be used is to rule out a phenomena. As I recall, Nosworthy and Galt and Harold were trying to work out whether they had seen a satellite to Arecibo, and what they had to do was rule out other possibilities. So it is quite possible for an effect to someone to have a light curve in which there is a gradual transition that they didn't expect. And the question will then be, so what did that? Is that diffraction, or no, is that perhaps some atmosphere of the object that I'm observing? And in that case, you've got a model which allows you to calculate the diffraction effect, and you can say, oh yeah, wow, yeah, that's just diffraction, or you can rule it out. And I think that that is probably the most common way in which this tool will be used. I'm going to stop sharing at this point and turn this over to any other questions that people might have.
This is Wayne Thomas, and I have a question on your last slide. It would appear that the R was not symmetric with the D. Can you comment on that?
Well, that's because of the effect of the camera integration. The camera integration produces that asymmetry.
Can I make a comment and a request?
Sure.
Fresnel diffraction is an interesting issue which has concerned me for quite a few decades, and I don't claim to understand it all. I've known that Fresnel diffraction around circular objects and so forth is not straightforward, and I'm very impressed with what you've done. You mentioned you've got some sort of demonstration program. I would love to see that, and if you're willing to see the code behind it, I'd like to include something like that in a cult if that was okay.
Dave, I haven't packaged that program up in a way that I could easily do that, but I want to do that. We'll have to work out how that would best be fit into occult. As you know, I do this code in Python, but I think we could work offline to do that. No, I'd be really happy to undertake that project.
It's very good. Now, the other thing, and I'll share my screen just to show people something. If I get the screen. In Occult, I already have a basic Fresnel diffraction predictor, if you like. This is just a random event. Can people see this screen?
It's a bit small in my display. If you can just kind of zoom that up.
I'll see what I can. It's not going to do that. I've got a high resolution monitor. That's just a prediction map. I have two things to indicate this. One is at the top, I have information about the star diameter, and if it's significant, I'll put something about fades of a certain duration can be expected. But I also have a function which you get from a right click of display stars diameter and Fresnel diffraction. And this is what comes up for this event. And I've did this from Raymond Duss's stuff that he did many decades or several decades ago before he passed away. In that form gives an estimate of the star's diameter, and 90%, 95% of the stars, the diameters are less than 0.1 of a milliarc second. And then for Fresnel diffraction, I've got a list of expected durations on a central line in the context of a magnitude drop, which I sort of hope it's right. So in this one, for this particular event, for a light drop of 2 magnitudes, expect 0.2 milliarc seconds and relate that into a time. And with this one, because the asteroid's moving so fast, the duration is always 0. If I go into here we go. I'll pick another event and display this information. It's not showing up what I would like, so I'll finish sharing that screen. I guess the point I'm indicating is that there is something in Occult. It is very, very basic, but this is at the prediction side, and well, I would like to expand that, and I very much appreciate being able to tap into your work.
I'd be happy to do that. I suspect that what you have there is actually adequate.
Bob, Ted Blank, quick question. You mentioned that there's the ability to enter your offset from the center line.
Yes.
Many times, as you know, what you think your offset from the center line is turns out to be far from accurate because the shadow may move. You might think you're on the center line and end up on the edge, or vice versa. So would you recommend that we wait until a few other observations come in so we can know exactly where the path might have shifted to before using that offset value?
Well, if you have a single chord observation, you have some idea where you are relative to the center line by the duration that you see. So if you expected, a 4-second event and you got a 2-second event, you can do a little bit of trigonometry and figure out roughly how far you were off the center line. And that graze effect, until it is very close to the edge, is a very, very secondary correction to the timing. So it is not that critical. A lot of what I have talked about here is just kind of like refinement on top of refinement. So I wouldn't worry too much about getting your center line offset to 2 decimal places. It's just not that critical.
Understood. Okay, thank you.
Can you comment on the difference between the diffraction methodology in PyOTE versus the penumbral light curve methodology? There's another feature there that you didn't mention.
Well, in a penumbral light curve, you've got a disk occulting a disk, and you're not normally taking into account diffraction effects in that. That's a completely different light curve in which you're not going to see diffraction effects anyway. You don't have a point source. You had a finite star disk. It's not a point source anymore. Your diffraction disappears almost completely when you've got a finite disk of a star. I did demonstrate that, how the diffraction effects disappear almost completely when there is a finite star disk, and a penumbral curve comes from the interaction between the asteroid disk and the star disk.
Right. So yeah. So when a user sees a gradual edge or a gradual transition between baseline and event bottom, it doesn't necessarily mean that diffraction is appropriate. You may need to use a penumbral solution in PyOTE, correct?
Yes. You may also be seeing a Pluto atmosphere effect. So there are multiple reasons why there will be a gradual transition, and there'll be points in the transition zone, and you need to be able to sort those out. And that just simply requires expertise in knowing what the effects are, being able to calculate the magnitude or the more precisely what the effects might be, so that you can either rule out or rule in whether diffraction is a cause, or whether no, we got to look at something else.
Just one comment on that. A critical issue for that is the expected star diameter, and comparing the effects of the star diameter things with the Fresnel diffraction effects. And as I indicated before, most stars have a diameter that's down 0.01 milliarc seconds or less typically. But then when you get red giants, then the star diameter becomes very, very significant. And I would sort of suggest that in terms of distinguishing between the two, you do need to have a look at what you expect the star diameter is to assist in making those decisions.
Yeah, in doing some of my work, I referenced occult, and I looked at some of the star diameters that you were reporting there. So yeah, I'm quite familiar with that.
Yep.
We really need to move on if we can.